won't be here in next class, you'll just do the same thing, just watch the video. Anyway, let's start talking about the history of the atomic model. So it all starts with Democritus, one of the ancient Greeks. He proposed that all matter consists of extremely small particles that cannot be divided. And he called them atoms, from the Greek atomos, meaning indivisible. This might not sound too crazy now, but at the time, they didn't understand really much about the world around them. So if you imagine, they held a stick and broke it in half, and then you could break it in half again, break it in half again, break it in half again. Now, at some point, you're not going to be able to physically break it in half again, but why should there ever be a point where you can't physically break it apart again? So this is kind of what Democritus first proposed, that there was this certain point where, after this certain point, you just can't break it apart anymore. However, Democritus had no evidence for this. He obviously didn't have, any kind of microscope, so people didn't really believe him. This is Aristotle, famous philosopher. And Aristotle said that's ridiculous. Why would there ever be a point at which you can't break it down? And people tended to believe Aristotle. Aristotle believed all matter was made up of 4 elements. Anyone know what the 4 Greek elements that made everything up were?
Water.
Water is one of them. Earth.
Fire.
Wind. Air or wind. Right, those are the 4 Greek elements. Earth, water, air, and fire. And they pretty much thought everything was sort of a combination of those two. For example, if something was hot, it was a mixture of fire and air. If something was dry, it was a mixture of fire and earth. If something was cold, it was a mixture of water and earth. And if something was wet, it was a mixture of air and water. Because at the time, they didn't really know much else. And for centuries, people believed this. We had no evidence to say otherwise. Until the 1800s came around. That's when we started developing more of a knowledge of the world around us. So the first major player in the atomic model is John Dalton. John Dalton, an English scientist. He used evidence from gas experiments to propose his atomic theory. First, all elements are composed of atoms. Second, all atoms of the same element have the same mass. Atoms of different elements have different masses. 3, compounds contain atoms of more than one element. And 4, in a particular compound, atoms of different elements always combine in the same proportions. So you could fill in those blanks there under Dalton. Now this was proposed in 1803. Some of these still hold true today. Let's go through each one, and we haven't really gone over everything in detail, but let's just kind of see if we can prove or disprove some of these. So number 1, all elements are composed of atoms. Is that true today? Yeah, it's still true. Number 2, all atoms of the same element have the same mass. Is that true? No, it's not. Can you tell me, an example? Can you elaborate on that? Anyone? What do we call elements that have different masses? For example, isotopes. We'll get to that a little later. Not every carbon atom has the same mass. Not every oxygen atom has the same mass. We call those isotopes. And atoms of different elements have different masses. That's obviously true. Number 3 says compounds contain atoms of more than one element. Is that still true? Yep, the true definition of a compound is 2 different elements. I mean, we know there are things like molecules, like O2, H2, the same element. And number 4, in a particular compound, atoms of different elements always combine in the same proportions. Is that true? That is true. We actually talked about that early on this year. It's the law of definite proportions. What that means is water is always H2O. Carbon dioxide is always CO2. Now, that's not to say that carbon and oxygen can't form different things. That's the law of multiple proportions, meaning carbon and oxygen can form CO2, CO. That's basically it. You're not going to really get any other combinations. But things like, H and O can form OH, hydroxide. They can form H3O, hydronium. Well, that would be a plus. They could form water. They could form H2O2, peroxide. Okay, so a lot of these are still true today. And most of this was based on his simple experiments, which basically involved crude balloons that he filled with gases. Thinking back to Dalton's law of partial pressure, that involved gases. This is a picture of Dalton's model of the atom. This is 3 of them. Basically, he proposed that the atom is a solid sphere or a billiard ball. He just said it's one round object. And this picture is actually from the London Museum of Science, because these are his original prototypes. I think I found some other photos too. Yeah. So these are some more examples of Dalton's wooden spheres. He basically proposed that atoms are just single sort of units like that. So at the bottom I say sketch Dalton's solid sphere, aka billiard ball model. Pretty much just draw a circle. You can put like a little shadow to make it a sphere. But that's basically all he thought. It was a solid particle. So yeah, just basically draw a circle, or if you're an amazing artist, you can try to depict a sphere. By the way, these holes that you see in them, he didn't propose that they had holes. The holes were basically he could put like a wooden peg in and attach them together. So like this was like a compound that he proposed. This could probably be something like water with 2 H's and 1 O. Okay, moving on. The next major step was from Joseph John, who was called J.J. Thompson. He performed experiments using a cathode ray tube. Let me just go over what a cathode ray tube is. First of all, has anyone heard of a television referred to as the tube? Yeah, really old TVs. Well, back before everything was, plasma and HD and flat screen, TVs were basically, these cathode ray tubes. So in a basic cathode ray tube, you take a chamber like this, and you create a vacuum inside. What does that mean? How do you make a vacuum? Pull all the air out. So you pull all the air out. So I'll put here vacuum. So there's no air. You put 2 electrodes here, which are basically 2 little nodes that one of them creates a positive voltage, one creates a negative voltage, like this. So we can say a plus here and a negative here. And you have some kind of battery power, which is symbolized like that. So it's basically trying to conduct a current through nothing, through a vacuum. And people had noticed that when you hook this up, you saw a very faint, beam of light. Now I'm going to show a video of what this actually looks like today. But what you got to understand is that today, in 2015, we can create a very perfect vacuum. Back in 1810, when Thompson was working, they basically hand pumped the air out of this chamber, so it was obviously not a perfect vacuum. So what you're going to see in this video is definitely not what Thompson saw, but it's still enough to see where he kind of drew his ideas from. So let's take a look here. Start this up.
Okay, this is a cathode ray tube. What it essentially is, it's a vacuum chamber. There are no gases inside this glass tube. The only thing we have are 2 electrodes, one's called the cathode, the other's called the anode, and a fluorescent screen in the background. It's coated with some type of fluorescent material. When I turn the power supply on, we'll see a beam that causes that fluorescent screen to glow. Looks like a nice straight line, doesn't it? We call that a cathode ray because it emanates or begins at the cathode and shoots across over to the anode. J.J. Thompson was working with cathode rays. We really didn't understand what they were. I mean, we have electricity going in one side and coming out the other, but there's nothing inside to conduct it. It's a vacuum tube. So he decided to apply a magnetic field to this cathode ray, and he found something interesting. We apply one pole of the magnet to this beam, and we'll see what it does, and then we'll flip it around and see what the other pole does. This is my favorite part. Can you see what's happening to that beam? What does appear as though it's happening to it? It's moving, it's being repelled, isn't it, by the magnet? When we flip the magnet around, and what do you think is going to happen this time? Well, if it's being attracted on one pole, see how it's being attracted there? Let me rotate it so the kids on this side of the room can see it. See how it's being attracted there? And then the other pole, do you see how it's being pushed down? What does that tell me about that beam? It has a what? It has a charge. Let me tell you about the poles of the magnet. The one that pushes it away is the negative pole. So what does that tell you about the charge of those particles? Negatively?
So that's basically what Rutherford, or what, Thomson was able to do. Someone hit that light, please. Go. Someone, please. So again, Thomson wasn't dealing with this like beautifully perfect beam of light. He was working with the tools he had available to him. But he did realize that he had this beam flowing through here, and that it must have been charged, and he realized this was a negative charge. By the way, at the time, people kind of had these ideas about what made up the universe around them. One idea that they sort of had was this idea of the ethos, E-T-H-O-S, as this like, almost like a material that's in the air around us, but we never feel it. Because they didn't think electricity could flow without something to conduct it, and since they pulled all the air out, they assumed that it was this ethos material, which was later disproven. But either way, this is what Thomson observed. Now, they were negatively charged, so that goes in one of your bullet points here. The particles were negatively charged. And he found that they were 2,000 times smaller than a hydrogen atom. He was able to figure this out through calculations. Basically, if you guys move on to physics, you'll learn some of the calculations involved in charges. But if you know the power of a charge, you can trace that all the way back to find the mass of the particle that's giving off the charge. So he worked through all these calculations, and he found that the particles that were moving were 2,000 times smaller than a hydrogen atom. Well, what was the problem with that? Because at the time, we assumed that atoms were solid, right? So if he discovered something smaller than an atom, he must have basically disproven Dalton's sphere. So he concluded that they must contain tiny negatively charged particles. Thus, he had discovered the first subatomic particle, what's this, the negatively charged particle? Electron. So he discovered the electron. Okay, so here's another look at a cathode ray tube. Basically two charged anodes with a vacuum in the middle. And this was Thomson's plum pudding model. Basically, Thomson knew that atoms must have contained these particles that were negatively charged. However, he also knew that atoms themselves had no charge because, not everything in the universe stuck to a magnet. So he said, well, if they have negative particles inside of them, but the entire thing is neutral, the rest of the atom must be positively charged. So basically, it's negative electrons moving around in a sea of positive charge, or almost like a positive sort of ooze. Plum pudding, by the way, was a very popular dessert. This can also be called the chocolate chip cookie model. But either way, it featured electrons in sort of this ooze of positive charge. So please sketch this one below if you haven't already. Okay, the next major step in the development of the atom came from Ernest Rutherford. By the way, I don't think I mentioned Thompson was also English, so far it's two English scientists. Rutherford was English, like by blood, but he lived in New Zealand. He performed experiments using, sorry, I'm losing my place here. He basically studied radioactivity, which we know a lot about today, but they didn't really understand it at the time. They recognized that certain materials were kind of destructive, but they didn't really understand why. He worked with two students named Geiger and Marsden, both of whom went on to earn Nobel Prizes and make discoveries of their own. In fact, I want to pause here and talk about Geiger, who was just Rutherford's student. This here is a Vernier digital radiation monitor. Basically, a device that measures radiation is called a Geiger counter, named after Geiger. Okay? By the way, this was all discovered when Geiger and Marsden were basically undergrads. So a little note, if you're going on to college and studying science, get to know your professors, you could win a Nobel Prize. This is a Geiger counter, it measures radiation. Every time you hear the little click, there's some radiation. So fortunately, we're getting a couple little readings. Let's see, my computer, a couple little clicks here. So nothing too serious. But just to show that this does work, let me have everyone come up and sort of gather around here.
Are bananas extremely radioactive?
I have heard that. Anyone have a banana?
No.
Just kind of show the camera here too. So what I have is a sample that I got from the geology teachers across the way. Anyone want to take a guess what metal this is? I am protecting us from a radioactive source. What metal do they use for that? Definitely not mercury. If that were mercury, it would be spilling all over the floor. This is lead. You ever heard that those old fallout shelters were lined with lead? That's because lead stops radioactivity, or at least it stops gamma rays. So right now, we're getting some increased level of activity here, but nothing too serious. Now I'm going to lift this and expose the radioactive material, but don't worry, this stuff takes years of exposure to have any real effect. I'm just going to show it for a couple seconds. But basically this is a sample of a mineral. This is carnotite in sandstone. This was taken from Utah. And if I move the Geiger counter closer, you see that it's going crazy on this sample. So this is obviously producing a lot of radioactivity. And just to also kind of demonstrate why we use lead, I took some aluminum foil and wrapped it or folded it up a bunch of times. Let's see if that stops it. No, really no effect at all. But if I put the lead, it just shuts it down. Okay, so this is a Geiger counter. It's used to measure radiation. And I'm going to put this back. And I'm really just wearing the gloves, not for the radiation. It's really because you don't want to be touching lead. This stuff, by the way, is pretty neat. It folds very easily like this. So you can actually conform it to make a little hut for whatever sample you work with. If anyone's going to be moving on to geology here, you'll be dealing with this stuff a lot. Okay, so you can grab a seat. Just wanted to go over our radioactive samples. All right. So anyway, Rutherford had two students, and they were all studying radioactivity together. This was his basic experiment. Now, this doesn't really do it justice. I'll kind of show a little animation for you. He took a thin sheet of gold, which is what you see in that little yellow square, and he was able to basically fire a stream of radioactive particles, which were alpha particles, at this. And let me just sort of show this again real quick. Alright, so imagine this is gold here. Oops. Thin sheet of gold. He fired these particles at him. Now I'm going to represent them like this. But in reality, these are called alpha particles. Which is a type of radiation. Let's see if this picks it up. Yep, detects alpha, beta, gamma, and X radiation. Alpha particles are sort of the least dangerous. I think bananas definitely emit a lot of alpha particles. I've had one of these when I was student taught. We had a Geiger counter that just focused on alpha particles, and you basically detected it everywhere. So alpha particles are really not that dangerous. What an alpha particle consists of is, we know this now, we didn't know it at the time. It's 2 protons attached to 2 neutrons. In other words, it's a helium nucleus. So if you take a helium and strip the electrons off, you produce an alpha particle. Now this obviously has a positive charge. This is very dense too. Without the electrons, it's like a tiny little, it's almost like a bullet with a positive charge. And he was firing them through this sheet of gold. Now at the time, they thought that this is what the atom looked like. A sea of positive charge with tiny little negative electrons floating through it. Because this is so concentrated with its positive charge, they thought it would basically shoot through just like a bullet. Maybe a little bit of skew, like it could maybe go like off to the side a little bit, maybe off to the side a little bit like this, but mostly they thought they would just pass straight through. So let's take a look at what actually happened.
In the early 1900s, J.J. Thompson proposed that an atom was a uniform sphere of positively charged matter in which electrons were embedded. This model is sometimes called the Plum pudding model. Electrons are embedded in a sphere of positive matter, similar to raisins in plum pudding. In 1910, Ernest Rutherford, Hans Geiger, and Ernest Marsden carried out experiments in which very thin foils of metal were used as targets for alpha particles emitted from a radioactive source. Click on what Rutherford expected to observe the results Rutherford expected.
So again, this was
Based
the
on
alpha particle
Thompson's model,
emitter.
Rutherford expected that the positively charged alpha particles should pass through the uniform sphere of positively charged matter with little or no deflection. Click on actual experimental results to see what actually happens. Rutherford observed that the majority of alpha particles penetrated the foil either undeflected or with only a slight deflection. Every now and then, however, an alpha particle was scattered or deflected at a large angle. In some instances, an alpha particle actually bounced back in the direction from which it had come. This was a most surprising finding, for in Thomson's model, the positive charge of the atom was so diffuse, or spread out, that the positive alpha particles were expected to pass through the foil with very little deflection. Upon making this discovery, Rutherford exclaimed, "It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you." Click on Rutherford's model to see the model of the atom that Rutherford proposed based on his experimental observation.
Right. Just to sort of clarify, he thought it would pass through because the entire atom is just this like positive ooze, and if you fired like a positive bullet through it, which is basically what these particles are, it wouldn't be concentrated enough to deflect it. But it was really this, and the figure I read was about 1 in 10,000 particles deflected back. So like, 99 out of them just shot straight through, but every now and then one would pass back. And this was basically the model that he came up with.
Based on the results of his experiment, Rutherford postulated a nuclear atom. All of the positive charge and most of the mass of the atom is concentrated in a very small volume called the nucleus. Electrons occupy the remaining space of the atom. The radius of an atom is approximately 20,000.
Pause that. Basically, he said that in order for these atoms to deflect that positive alpha particle bullet that he shot through it, it must not be this sea of electrons that the positive ooze here. It must not be like this. In fact, all of that positive charge must be concentrated in this tiny point in the center of the atom, and we call that the nucleus. So basically, Rutherford had discovered the nucleus. So again, this is what he expected. He expected them to basically go straight through, maybe skew a little bit up or down. This is what actually happened. The vast majority passed straight through, but every now and then some of them would bounce back. And this is now the model of the atom. It's this tiny particle in the middle. You can't see it, that's like a bunch of little plus signs in the middle. And therefore the electrons must be moving around outside. Let's check our blanks here. So the top blank on the Rutherford should be positive charged particles were launched at a thin sheet of gold. Moving down near the bottom, Rutherford concluded that all of the positive charge and nearly all of the mass of an atom was located in a tiny nucleus. Not sure if he actually coined the term nucleus there, but that's what we call it today. Now as for the location of the electrons, he didn't really have an answer for exactly where they were. But he thought, well, if you imagine a tiny particle at the center with all of the mass, it's almost like outer space. So he kind of proposed, getting into Bohr, he basically proposed that the electrons moved around the nucleus like planets around the sun. Let's just sketch another image of the Rutherford model, which now incorporates a nucleus. So we have this tiny positive charge in the middle, and we have these electrons that move around like this. And what you'll see is that most of the new models after this, they talk more precisely about the electrons. Okay, so that's your Rutherford model, nucleus with electrons orbiting around it. And really, if you think about the atom, which particle, based on what we've talked about this year, which particle would you say is most important to study? Protons or the electrons, and why?
Electrons,
Why?
because it's like how they bond and
Exactly.
yeah.
Basically all the properties, other than like the density, has to do with the electrons. So what you'll see is that over the next 100 years, we learn more about the electrons, and that helped us learn more about everything else that we've studied. All right, and bottom blank here, he proposed electrons over the nucleus like planets around the sun. Rutherford's model of the atom, sketch it on the next page if you haven't already. Next scientist, Niels Bohr, Danish, from Denmark. Again, now we've basically discovered the nucleus. Everything now focuses on the electrons. He said, maybe instead of electrons orbiting the nucleus, they must only be stable at certain distances from the nucleus. And the reason this was a big discovery is that people said, okay, Rutherford, we believe you that electrons orbit the nucleus. But if you have a positive charge in the middle and you have negative charges orbiting it, why don't those electrons eventually circle closer and closer and closer and closer and closer, and then just like collide with the nucleus? And it's a good question. I mean, if you have a negative and a positive, why wouldn't the negative eventually work its way in? Well, Bohr worked out through calculations that electrons can only be stable at certain distances from the nucleus. And this is a very strange concept. This goes kind of beyond what we know about physics on the macro level. We learned that electrons have some physical properties, like they have mass, but they also have wave-like properties in that they can basically teleport. It's very strange, and it's one of those things that we're still discovering as the decades go on. But it all kind of started with Bohr. He said they can only be stable at certain distances from the nucleus. So this is where we get our Bohr model of the atom, which you guys probably looked at in bio. Nucleus in the middle, and we have these orbitals. And the electrons can only exist on these orbitals, never in the middle. And obviously this is definitely not to scale. These electrons are like 2,000 times smaller than the protons. And if you want to talk about the distances here, I don't have a true comparison, but what I believe I think it's if the nucleus were like the head of a pin in the middle of like a baseball stadium, the electrons would be like out in the bleachers, basically. There's a huge distance of space in between. Now, after we get through all this, the end of the week, this week, or early next week, we're going to go more into the Bohr model. But what you basically need to know is that these electrons can jump up or down in their levels, providing there's space for them. But when this one goes from level 1 to level 2, it physically moves itself. However, it never exists in between them. It's a very strange concept. It basically teleports, and that's one of the wave-like properties. Kind of one analogy I heard is if you have like a guitar and you hold your finger down on the string. If you like flick one side of the string, that wave will travel through the string onto the other side, and both sides will vibrate, but the side under your finger is never going to actually move. So energy and this sort of wave-like motion can transfer, but the particle never physically exists in the middle. Another way of thinking about it is imagine these are steps. You can be on the first step, you can be on the second step, you can be on the third step, but you can never be on the like 1.5 step. You have to be on one or the other. So that's Bohr. Another interesting story I heard about Bohr. Oh, question, Kat?
What was the second block?
Good point here. So the second block, electrons in orbit farther from nucleus have more energy. This is again something we'll talk about a little bit more later. This electron here has the lowest energy because it's closest to the nucleus. This one has the second lowest or the second highest. This one here has the highest energy. And when you give an atom energy by like giving it motion, like for example, if this atom's just sitting here slowly moving and another one collides with it, it's going to give it energy. It's going to cause the electrons to jump up. Another story I heard about Bohr, which I found really interesting. Bohr was a Danish scientist. And basically, a lot of these stories come from European scientists in the early to mid 1900s. Now, what was going on in Europe at that time? Like, it just early 1900s. Kind of both world wars, right? First one was 1914 through 18, second one was 39 through 45. Well, these scientists generally had this belief that the science should go on no matter what. Unfortunately, however you want to look back through your perspective, but the governments basically said, we need you on our side. So that's why a lot of these scientists, they had to like put down their research and work for the war, like producing things like missiles and like firearms. But for the most part, the research continued, and it really was like these scientists did. It's not like the German scientists hated the French scientists, and it's not like the Austrian scientists hated the British scientists. The scientists generally worked together and collaborated. Some of the other scientists we're going to see in this are Austrian and German. There were Japanese scientists that were working on improvements to the model of the atom. They all sort of worked together. But Bohr was a Danish scientist. Denmark was invaded by the Nazis, in the early 40s, and he knew that he had won a Nobel Prize. And when you win a Nobel Prize, you get like $1 million, which generally you donate to your university, and you get a solid gold medal to show your, it's like an honor. He knew that the Nazis would seize the gold medal and use it for the war effort. And there were also two other scientists in Denmark who sent him, they were actually in Germany. They smuggled their Nobel Prizes to Bohr, and they wanted him to somehow save them. Because they knew if the Nazis got hold of their gold, they would, melt it down, and make, you know, gold bars out of it for the war effort. So Bohr got these 3 Nobel Prizes, solid gold medals, and he tried to think of what kind of chemical way he could hide them. They thought about burying them, hiding them in like the rafters of their lab, and they realized nothing would work. So what he figured out what to do was to dissolve them and then recover the gold after the war. Look at the activity series. Where does gold tend to be? Near the top or bottom? Near the bottom, right? I kind of demonstrated putting the gold ring in the acid. So basically, Bohr had to come up with something that would dissolve the gold, and there's really only one thing. It's called aqua regia, which the name kind of means royal water. It's hydrochloric acid mixed with nitric acid, and that is able to dissolve gold. So he got this concoction. Let me show some pictures of it. It's a really neat story. He got aqua regia. He dissolved all 3 Nobel Prizes. See if this loads up. But anyway, you know, he dissolved them in this liquid, put it on the shelf, and the Nazis searched his lab because they knew he had gold Nobel Prizes, and they never found it. And then after the war, he just precipitated the gold back out. He sent it back to Stockholm, Sweden, which is where the Nobel Committee meets. They recreated the Nobel Prizes and sent them back. It's kind of a neat little story. Let's see if they're all right. So there's Bohr holding the sample. Yeah, it was Bohr. It was Max von Laue, who was a German scientist, and James Frank, another German scientist. These two, I believe one of them was Jewish too, so he was definitely going to be targeted by the Nazis. They both sent their Nobel Prizes to Bohr, and Bohr took care of them. This is a video of aqua regia.
All of it is converted to another acid, which is an acid of gold with 4 chlorine atoms round it. This material is then quite soluble in water, so provided you don't have too much gold, it will all dissolve. And once you have a solution,
You basically end up with the gold dissolved in aqua regia, and it changes the color of the material, but it's still gold. All right. Any more questions about Bohr? Okay, next we have Schrodinger and Heisenberg. If you're a Breaking Bad fan, Werner Heisenberg was the inspiration for the name Heisenberg. Schrodinger was Austrian, Heisenberg was German. And together they came up with the next step in our atomic model. Let's see where we are in the notes. Let's see. They proposed the electron cloud. The way I like to demonstrate the electron cloud is with a fan. So if this fan were to represent an atom, and each blade was 1 electron, how many blades in this fan? 5. So this is we'll call it a boron atom. 5 electrons. Right now, you can tell how many there are, and you can tell exactly where they are, right? It's easy. But if I turn it on, kind of point it away, can you still tell me how many there are in here? Right? There's still 5, but can you tell me where they are right now? Like exactly? Yeah, we know that they're somewhere in here, but it's impossible to tell exactly. You can't say like, oh, one's right there, right there, right there, right there. You can't ever know. And this relates to the atom because through our calculations, you can never really identify exactly where the electrons are, but we know how many there are, and we know the general vicinity they're most likely to be found in. It's sort of this uncertainty that we know. So really this is the electron cloud. The way you draw it is with your nucleus in the middle. Now remember, at the time, they didn't know about neutrons yet. So they thought the nucleus was just positive protons. So you draw your little tiny positive nucleus, and then you just sort of shade around the outside. and you try to get more shading near the middle because they're more likely to be found in the middle. They're less likely to be found out here. But all we know is that there are electrons in this general vicinity. Next. Now there are certainly other steps in between these. There's hundreds of little contributions people have made from all over the world, but I just kind of chose like the 6 major ones. James Chadwick, English scientist, he discovered the neutron, which is very important because after 1932, we started looking at creating atomic weapons. And it's sort of fortunate to us as Americans that Chadwick happened to be British, because if he were German, perhaps it wouldn't have been us dropping nukes during the war. Anyway, he discovered the neutron. Basically, he realized that the mass of certain elements could change, but the charges didn't. So in order for that to happen, there must be some heavy particle inside the nucleus that didn't have a charge. So let's just make sure we know what we're looking at here. Backside here, he discovered the neutron. Neutrons are found in the what? In the nucleus. They're about the same size as what? Anyone know? Proton. And they have what charge? No charge. You can say 0, you can say no. What I have on the next couple slides is basically looking back from our 2015 lens. Let's just sum up what we know about atoms. And really, this is nothing new. Atoms are made up of protons, neutrons, and electrons. Protons have a positive charge. A little typo there, so say charge, not charged. Neutrons have no charge. Protons and neutrons make up the nucleus in the center of the atom. Let's try to fill out the other blanks without even looking up here. So the next blank says electrons have a blank charge. What would that be? Negative charge. Next one says the nucleus contains nearly all of the atom's blank. Mass. Protons and neutrons both have around, the answer is 1,800 times. 1,800 times more mass than the electrons. Electrons are located in the electron cloud, an area that surrounds and is much larger than the nucleus. We usually depict atoms looking like this, you know, with your nucleus here and your electrons here. If this were real and something I do in physical science, I might, maybe by the end of the week I could do it here too. We actually model what a scale atom looks like. So I'll hold like little clay circles represent my protons and neutrons, and then we'll work out the calculations for how small the electrons are and where they're actually located. And it's pretty interesting. I think when I did it before, you hold I did like a carbon atom, so 6 protons, 6 neutrons, and you know it was about the size of a baseball when I put it all together, the nucleus. And the electrons were, let me ask, if I held a baseball-sized carbon nucleus, where do you think the extent of the electrons would reach? Like let's say I held it right here in the middle of this room. Any guesses? How far outside? First of all, it would definitely be outside this room. So, like, according to that model, that little picture right there, like, if the nucleus were here, like, the electrons would be, like, here, that's definitely wrong. They would certainly be outside this room. How far out do we think?
Clue center.
Farther. Outside the building.
Located.
Lily Field.
The basic figure that we found was about 1 mile. So if I held like a baseball-sized nucleus here, the farthest extent of the electrons would be about 1 mile away. And they would be basically, like imagine a little sphere of clay like 1 millimeter in diameter. It's like that small. Now that's not where they always are. but that's like the max extent. Remember, according to the electron cloud, we know the electrons are somewhere inside that 1 mile radius, but we can never tell exactly where they are. We just know they're somewhere in there. It's pretty neat too, because if you think about the floor I'm standing on, it's the vast majority of it is empty space. It's these tiny nuclei with electrons so far away, and yet you don't fall through the floor, and yet this table doesn't dissolve into the air. It's just because even though they're so small, the charges are so powerful that everything's held together through electricity, basically. Positive and negative charges. Okay, any questions about the models of the atom? Alright, let's move on. So I think we've finished the notes here. So you can kind of copy the rest of this in the bottom of the notes or on a separate sheet. We'll go for 10 more minutes. And again, a lot of this stuff should be review. First of all, what's the atomic number? Number of protons. We look at the atomic number, which is the number of protons. And this is how we identify an atom. The actual definition of a hydrogen atom is an atom with 1 proton. The actual definition of a helium atom is an atom with 2 protons. And it goes on from there. Now what you saw emitting from that particle, well, you didn't see it, but what you heard emitting from that little sample of rock was uranium, which underwent radiation, and it produced a different element. So really, the uranium will split into 2 smaller ones, and by splitting, when the number of protons changes, the identity of the atom changes. Okay. Atomic number is the number of protons. For example, every atom with 2 protons is a what atom? 2 protons. Which atom always has 2 protons? Which element? Dane?
Helium.
Helium, right. Not a trick question. Every atom with 2 protons is a helium atom. Every atom with 6 protons is a carbon atom. Every atom with 8 protons is an oxygen. So that's just how we define what an element actually is. And we organize them by their atomic number. Today we do this. When the periodic table first came into being, they didn't understand the concept of an atomic number because they couldn't count the protons. So they organized them by the weight. Now this generally follows through, but there are some cases where the mass kind of drops. For example, argon into potassium, the mass sort of drops out. Let's talk about mass number. This is different from atomic number. The sum of the number of protons and neutrons is called the mass number. You take the protons, add it to the neutrons, and that's our mass number. Okay, so for example, a fluorine atom with 9 protons and 10 neutrons has a mass number of 19. You don't even really need to go through these. 23. 1 proton and 0 neutrons has a mass number of 1. That's your average hydrogen atom. Has a mass number of 1 because it's just 1 proton with 1 little electron. Okay. Again, from here, if we know the mass number and the atomic number, we can find the number of neutrons. So this is your basic formula. Number of neutrons equals mass number minus atomic number. Just simple subtraction. Mass number minus atomic number. So for example, if I told you a carbon atom has a mass number of 11, how many neutrons are in that carbon atom? How can we tell? What do we know about all carbons? They have how many protons? 6. So if it has 6 protons, how many neutrons must this one have? 8, right? So So it's, nothing too crazy. If you know the mass number, look at the periodic table, you can find the number of neutrons. Let's talk about isotopes, which we sort of mentioned earlier. Not all atoms of an element have the same number of neutrons. Atoms of the same element that have different numbers of neutrons are called isotopes. Okay. The way we write isotopes out, we say the element, actually this is kind of a typo here. You generally say the symbol, not the name, then a dash, and then the mass number. Symbol, then a dash, then the mass number. Oops. For example, oxygen with 8 protons and 8 neutrons. You would write O, then a dash, and then what's the mass number of that? 16. So that is protons plus neutrons, 8 plus 8. So that would be O-16. Next one would be O-18. Next one, helium with 2 protons and 1 neutron would be He-what? 3. He-4. And then for uranium, you would have to add all that up. That's going to be U-235, which the reason I randomly jumped from helium to uranium is pretty important when it comes to radioactivity. You often hear about uranium when they talk about like weaponized uranium. It's a big issue in Iran right now. They're claiming that they want to use uranium to have nuclear power plants, and why shouldn't they? Well, the thing with uranium is if you enrich it enough, you can create weapons from it. So a lot of the international community is saying, well, we're not going to allow you to have uranium because we worry you're going to make a nuke. They say, well, you guys have it, why can't we? Big political issue. Anyway, uranium-235 is the unstable or the dangerous one. Uranium with 92 and 146, that's U-238, which is the safe one. Well, not really safe. It's radioactive, but in order to make nuclear power, you need to enrich it to about 10% U-235. That's enough to kind of keep the reaction going. If you want to make a missile out of it and bomb something, you need to make it 90% pure. So it takes a lot of energy to enrich it. Radioactive isotopes. Many isotopes are unstable. An unstable atom can emit particles or even change neutrons into protons to become more stable. This is known as radioactivity. Let me switch to the smart notebook and I'll kind of sketch this. All right, so imagine you have a nucleus. Let's do a carbon nucleus. 1, 2, 3, 4, 5, 6 protons. Most carbons have 6 neutrons, which I'll draw as just regular circles. 2, 3, 4, 5, 6. Now there's no real boundary here. We kind of represent that. Not like there's a shell around it or anything like that. Has anyone ever wondered why these protons are hanging together in the same place? What normally happens if you take 2 positive particles and hold them together? They repel, right? So why would this nucleus hold together? Anyone know? Well, it's because there's really a different sort of force in place here. They say there's 4 fundamental forces that hold our universe together. One of them is we call electromagnetic repulsion, which is a fancy way of saying positive and negative charges. However, there's a second one, and it's called the strong nuclear force. It's a very strange concept, and the way I like to think of it as, it's just like nuclear crazy glue. It is strong enough to hold these positives together, even though they are trying so hard to repel each other. Anything within this range of the strong nuclear force is just held in place. Okay? However, strong nuclear force, it is very strong, but limited range. So this can be like a representation. Anything that's held within this is going to hold together very strong. However, carbon, let's move up. Nitrogen, oxygen, fluorine. Does anyone see the problem? What's going to happen when these get bigger and bigger? Eventually it's going to fill this and it's going to reach beyond. So let's say I add so many in here, this is now full, and let's say I add a proton here and another proton here. This is when we start getting into these really heavy elements. Well, all of a sudden, this proton is held in place by the strong nuclear force. However, this one here is too far away. So the strong nuclear force is not holding these two together. In fact, this one is now repelling this one very strongly. If we add another one, it's even stronger. Add another, it's even stronger. By the time you get to U-235, it's going to be way out here. The reason that heavy elements break up is because the repulsive forces of all these protons is too strong for this nuclear force. So as you get to larger elements, eventually they will break up. Okay, and that's basically radioactivity. Okay, so we'll pause there for today. You got a couple minutes to relax.